this session is MoRE Shadow Walker, the progression of TLB-Splitting on x86 by Jacob Torrey. Give him a round of applause. Thank you.
Morning, my name is Jacob Torrey. I'll be showing you how Shadow Walker and a few other tools have been used and kind of show the evolution of TLB splitting and also what TLB splitting is for those of you who don't already know and how it's evolved over the years. You're welcome to follow me on Twitter. I know I'm figuratively standing in between you and lunch or the fun that will be standing in line for your DEF CON badge right after this. So I appreciate you being here and taking the time out. So really quickly about me, I lead a group of researchers out in Denver for a company called AIS. We do really low-level stuff, so since I've been there, I've written SMM handler / rootkit, my own BIOS, hypervisor, that kind of stuff. And I like the outdoors as well. That's why I moved out to Denver. A couple pre-talk notes. I cover some very technical stuff, so if I'm not making myself clear at any time, please feel free to jump in politely, and I'm happy to clarify. The rotten fruit and the heckling session, that will be saved towards the end. I have a slide for that. And I only speak for me, myself, and I, none of the people I mention here. So let's go on. So I'm going to give a little bit of background about what TLB splitting is, how it works, and then a little bit more about what the operating system and how x86 kind of supports the operating system in keeping you guys safe from rogue applications and malware, or doesn't, as the case might be. A little bit of history about PAX and GR security, a defensive tool back from 2000. Shadow Walker, an offensive tool from about 2005. And then some of the work that I've done for a DARPA Cyber Fast Track program. And then swinging that to the offensive. This is Black Hat after all. So I'll draw some conclusions and wrap up. So then we can all get some food or head to the bar. So this is going to be pretty basic for a lot of you, but I just wanted to make sure I had it covered just for those of you who might not be so aware. x86, which is the Intel processor commonly found in your laptops and desktops, supports different rings of protection. So ring 3 is the least privileged, it's the outermost ring. That's where your user applications are going to sit. Rings 1 and 2 currently are not really used. Like Minix is kind of a more academic one. They use rings 1 and 2, but we'll just ignore those. Ring 0 is traditionally considered your kernel, so that's where Windows or Linux will sit. And then ring -1 is a newer name for the hypervisor. So it's been added much later, but it has more privilege than the operating system kernel. If you want to keep going down, there's also ring -2, which is system management mode. Again, more privileged, but sorry. So I'm going to start off again basic. We're going to assume that most of you guys know this, but there's some x86 stuff that provides the capability of doing virtual memory. So on a 32-bit system, each application kind of lives in its own, but it assumes to be a 4 GB flat address space. And that application, then that address space, even if you don't have 4 GB of memory, the application thinks it does, and it can't operate and access memory that might be in the kernel space or another application. Before this happened, before this was added to the CPUs, back in DOS era, an application that went rogue, so to speak, could overwrite the DOS kernel and infect the entire system. So it's a protective measure coming out of the CPU that allows the operating system to improve its protection. For ways to break out of this, please see my article in POC or GTFO coming out on Friday. You can get a copy at the No Starch press booth in print, or you can download it at a mirror near you. So again, more on address translation. So this is how you actually go from a virtual memory address to a physical memory address. So your virtual address, so the pointer you access and see, consists essentially, that address is an offset into a table and then an offset into a page in the most simple case. So there's a register on the CPU, CR3, control register 3, that stores the physical address base of the page directory. This is usually kind of kept different for each application so they can have their own unique view of memory. And then that points to the page directory. So the first couple bits of your virtual pointer index into that, and then you get another part of an address, and then the next is the offset, which is used with the offset from your virtual pointer. And so that's how you can go from a virtual address to a physical address. This is a very simple example. I think if you had a full system with a hypervisor, etc., you could have up to 7 levels of indirection. This is really slow, as we know. Memory takes a long time to access compared to cache. And so if you're accessing 1 byte of memory from a certain page that hasn't been accessed recently, you're going to have to go get the page table, look through that, and get a pointer to the page, the next level, and kind of proceed back and forth. So you might be hitting RAM or waiting on RAM up to like 7 times. In this example here, it's only 2 or 3 times before you actually get that 1 byte of memory you wanted as an application. So the solution, the TLB, translation lookaside buffer. So this is essentially just a cache. So when you're accessing memory, is if it's already been accessed recently and then that's stored in the translation lookaside buffer, fantastic. You just use that mapping that's already stored there and you can proceed. Otherwise, you walk through the tables and then you save that mapping and you proceed. So this is how everything is advertised if you read the software manuals or if you read some of the tutorials online. But in order to actually optimize this, so this is going from a logical TLB, is a logical unit in how the CPU works. If you're going to go and actually look at that, if you take a CPU and look at it in an X-ray or whatnot, you're actually going to see 2 TLBs, if not more. And so you're going to have a data TLB, which is closer to your data caches, and then you're going to have an instruction TLB, which is closer to your instruction caches and all your instruction fetch logic. They operate in sync 100% of the time. So it's essentially a von Neumann-esque architecture. So your view of memory, if you're looking at it as data and as code, are going to be this consistent. So this makes perfect sense for most of you. If you access virtual address 0x1000, and you read that instruction and you just assemble the first instruction and then you jump to it, you're actually going to execute that. What we're going to talk about today is desynchronizing or splitting the TLB. So in Shadow Walker or PAX, you'll see in the second diagram that your data TLB will point to a different region of memory than your instruction TLB. So this kind of gets into that more of a Harvard architecture. So if you guys play with some embedded stuff, AVR is a Harvard architecture. So what might be at pointer 1000, if you read it as data, would be different than if you actually jump to it. And so you'll see how this is used for both good and ill throughout the talk. Here I've shamelessly stolen a block diagram from the Intel software developer manuals showing that, in highlighted in red, you have an instruction TLB and a data TLB. And in pre-Nehalem architectures, this is what this talk is covering so far. So this is up to and including Core 2 Duo. So this right here is the procedure for how to actually do the split. So what you're going to do is you're going to trap on some kind of fault. So a page fault handler or a general protection fault. You're going to determine if that fault happened because of a data or an instruction fetch. So there's a couple different ways you can do that. If it's a page fault, there's an exit condition that's pushed on the stack that says if it's data or instruction. Or you can check the EIP and the faulting address in CR2. You can figure that out essentially. And then you prime the proper TLB by either setting data access bits in the page tables and then reading through that to put that memory into that mapping into the data TLB, or you can set the trap flag, which will put the CPU into single stepping mode, and then execute that one instruction that was faulting, which will then prime the ITLB or the instruction TLB. And then what you're going to do is you're going to clear the bit so it will trap back to you again, but you're going to leave it in the TLB. So you're not going to flush the TLB. So now you're basically desynchronizing what's in the page tables and what's in the TLB. And so the TLB, next time a program accesses that page, if it's still in the TLB, it will run through and point to wherever you pointed it to. And if it's not, if it gets cleared out because some other mapping has taken its place, it'll jump back and you'll have to repeat this process. Are there any questions yet? I know this is pretty low-level stuff. I gave a talk at B-Sides and no one asked any questions, and then as soon as I said, okay, thanks, everyone got up and formed a line to ask me clarifying questions because they were too embarrassed. So please, if you have a question, jump in. If not, yeah. Sure. So the question is why is it different from data and instruction cache? So when you're priming the data cache, all you need to do is access memory at data, as data, so by doing like a move EAX from that address, and that will go through the data fetch logic, and it will prime the data TLB. And so you can do that right in the kernel. It's very easy to do. And then to do it, and so usually what you're doing here is that you're paging out the memory in the page table so it will fault to you. That's the kind of the first step. That's how you get the trapping. And then you're going to determine, which I mentioned already, whether it's data or instruction. And then what you're going to do is you're going to update where the next kind of, where the actual memory page is in the page entry. So if you're splitting it, you know, for data is going to go to address 2000 and instructions are going to go to address 1000, then you're going to update that accordingly and then either access data, which will then prime the data TLB, or you'll execute that one instruction, which will do an instruction fetch, and then it will go through and it will prime the ITLB. And then you're going to set the page tables back to not present so that once it kind of gets cleared out of the TLB, you're going to come back and you're going to have to repeat this process once the cache runs out. Yeah, so this is running as either a page fault handler or a general protection fault. This is all happening in the kernel right now. Thank you. All right, some history. So 2000, PAX, GR Security, they came out with something called Page Exec. So that's, if you're not familiar with PAX, it's pretty impressive stuff. It's a set of Linux kernel patches that kind of improve security, and they've stopped stuff that, you know, people like the Futex bug and stuff like that. They've had some defenses against that, like from way, way long ago. And so the one we're going to talk about is there a capability called Page Exec. And so what that was is it was a set of patches that allow you to emulate the no execute bit on systems that didn't actually have the no execute bit hardware. So if you're not familiar, no execute is exactly what it sounds like. You can say if you have the stack address, the stack page, you can mark as no execute, which basically breaks the traditional kind of old school smashing attack attempt. So, you know, in your buffer overflow, what you're going to do is you're going to load some shellcode onto the stack. You're going to control the return address pointer. You're going to go back and execute that on the stack. So the no execute bit on modern systems will prevent that from happening, which has kind of driven the move to return-oriented programming, return to libc attacks, because that way you're not actually executing on the stack. You're just controlling execution to go to other locations for you. How they did this was brilliant. So what they did is they actually overloaded the user supervisor bit, which is not used all that much. And so user, we're talking about ring 3, and supervisor would be ring 0. So essentially what they did is that by default the pages would be in supervisor bit mode or paged out. And then when the application would come and try to execute this page, it would see that it was not paged out. It would go in, it would cause a general protection fault. And then it would be able to identify, okay, either this is if it was a data request, it would set the user bit and allow it to go through and it would prime that data TLB. And if it was an instruction fetch request, it would say, okay, so this is being violated. Someone is trying to execute on a no execute bit page, and it would terminate the program, you know, log, whatever it needed to do. And so this allowed you to actually, you know, add these protections kind of later. Yeah? Repeat the question. Yes, you don't set it explicitly. You don't either prime the data TLB. There's no different instructions to prime either the data TLB or prime the instruction TLB. You're doing that kind of transparently by either accessing data through the data fetch logic, which will defaultly, you know, which will automatically prime that. Usually just by accessing memory, it will happen in the memory management unit, so you don't really control that. Other processor types like Spark, you can actually write T codes and you can change how that logic is done, but on x86 it just happens, it's in the microcode. Yep. This worked on pre-Nehalem CPUs. There's really no point for it now because almost all systems have no execute bit done in hardware. Saves you some performance stuff. And then the nice thing about this from a performance standpoint is that since you're caching the TLB, every time that application accesses that page's data, so the stack, every time they push or pop from the stack, it's going to be in the cache and it's not going to have to go through this whole process until it falls out. Jumping ahead 5 years and swinging from a defensive capability to an offensive capability, Jamie Butler and Sherry Sparks came out with the Shadow Walker rootkit. Pretty well known. I'm guessing probably some of you have heard of it. It was a memory hiding rootkit. So rather than just denying access to, say, an instruction fetch versus data fetch, it actually pointed where the memory was accessed to different locations. And so originally it was protecting the FU rootkit. And so what it would do is it would split the TLB so that if there was some antivirus software out there that was scanning kernel memory and checking it against a known good signature or looking for an obvious patch or deviant, it would access the read-write version that was split and pointing to the legitimate kernel. But if you were to actually jump to that address, you'd be accessing the patched version, and then you'd be running the rootkit. And so it's a very clever way to kind of hide what was going on. And the only way to see it was to do some kind of behavioral analysis to see if the state had changed kind of while it was executing. So very clever, again, pre-Nehalem CPU. All good things must come to pass. Intel introduces the Nehalem architecture and actually breaks TLB splitting. They added a level 2 cache to the TLB, also known as an STLB or a shared TLB, which breaks the previous TLB splitting architecture. So what happens is you're going to have kind of just like a level 2 and a level 1 cache. When you write to the level 1 cache, it's also going to be saved to the level 2 cache. And then if it's not in the level 1 cache, it will go to level 2 cache before going out to main memory, or in this case, going to your fault handler. So what you're going to do is, say you're trying to prime the data TLB. You'll prime the data TLB, which will then also prime the shared TLB. And then when you try to kind of trap on an instruction fetch, the instruction TLB is going to ask the shared TLB before faulting and saying, hey, do you have a mapping for this? The shared TLB will say, sure do, here you go. And so that's why it breaks the system. Here's a block diagram, so you can kind of see how they've separated out where the data TLB and the ITLB are, and then highlighted in red is the shared TLB. Again, this is from the Intel software developer manuals. And so this really kind of screwed the pooch for a lot of stuff. I don't think I'd be standing here and telling you this if that was the end of the talk. I'd probably also have done a 20-minute talk rather than a 50-minute talk. So now I'm going to go through a little bit more background to kind of take you from where we are now to how we're able to do this now in new Nehalem and newer CPUs. So for that, we're going to need a few more technologies from Intel. So we're going to need EPT, which is the extended page tables. So these add an additional layer of translation. So now you're mapping not a virtual address to a physical address, you're mapping a guest physical to a machine physical. So if you can imagine splitting it up, each guest will run their translation from a virtual pointer to a physical pointer, and then it will run through the EPT page tables and go from that guest physical to the actual machine physical, which then goes out into RAM. Rather than triggering a page fault, it's going to trigger an EPT fault. That's a VM exit, so it goes right to the hypervisor. So now we're talking about hypervisor, not kernel. We're talking ring 0 or ring -1, not ring 0. And this has actually been really great. It's a great performance improvement. It allows the operating system to manage its own memory and do paging to disk and everything, and as if it was running on the native hardware. And it also really simplifies a hypervisor. Before that, you had to kind of implement a shadow TLB in your own, and it was really hairy and very frustrating. So EPT made that much faster and much better. It also implements some new instructions to clear selectively or on purpose entries in the TLB. So obviously when you're doing a context switch from one process to another, any mappings that were there, you want to have them invalidated. Otherwise, say if you're in a kernel context and you map in some sensitive piece of memory and then you switch to an application, unless that's invalidated, that application will be able to access that region of kernel memory. And so you can then explicitly remove some of that, or when you do a process switch and you change CR3, almost all the entries that aren't marked as stay here when you do a switch will get wiped. Of all this, the most important one to realize is that it supports execute-only permissions. This is going to be very critical going forwards. So it's a much more granular permission set. You have read-only, write-only, and execute-only, and then any combination thereof. So keep that in the back of your head as we go forward. The next technology they added is VPID, so that's VM Process ID. So that extends each line in the TLB with a tag, a numeric tag. So the VM ID of the The hypervisor, the VMM, is 0. Your first guess might be 1, the second guess might be 2, etc. And that prevents the TLB from being flushed every time you switch from either the guest to the hypervisor to the guest, or guest to guest. And that's really important because before this, just like when you have two processes switching, and you want to make sure that the TLB doesn't have mappings pointing to either the wrong place or to sensitive locations, the TLB would be completely wiped and flushed when you switch, when you VM exit or a VM resume. So what they did is they actually now, there's kind of like a sub TLB for each VM inside of the larger VM. And so you're kind of sharing some space there. So now our lookup diagram looks kind of like this. You access memory. Is the translation in the TLB and the VM IDs are correct? If so, fantastic, get your memory. Otherwise, go through and walk this. In between the get PDE and the cache stage is going to be walk EPT. So this is going to be another set of page tables that you're going to go through. But for simplicity's sake of the diagram, I'm just going to leave it like this. So now our new TLB splitting procedure looks something like this. So on an Inhalem new CPU, the TLB is split. You set up your EPT tables, and then you trap on EPT faults. You then do the same process of determining if it's an instruction fetch fault or a data fetch fault, and then you either set the page in the EPT, the entry, to either read-write, so data, or execute only. Then you need to set the trap flag to trap back to the hypervisor after one instruction, so you're going to single step the guest for one instruction. You re-inject back to the guest to let it run that one instruction to prime the proper VPID. So if you were just to do what you do in kernel space in Shadow Walker and you just read that data, you're going to prime the data TLB in the hypervisor context, not the guest context. So you'll be splitting yourself, not the guest, which is what, the way we set it up, that's how we had to architect that. And then we're going to reset the EPT tables back to no access essentially, so that if they get cleared out of the TLB, it'll come back and repeat this process. Then we can resume the guest, and it will just chug along. So that brings me to my Cyber Fast Track program, MoRE, measurement of running executables. So here we thought that we could use TLB desynchronization from Shadow Walker and PAX, that same kind of idea, to automatically separate data from instructions on like a shared memory page. So we were working in trusted computing at AIS, and so we wanted to be able to do real-time, on-demand trust of, say, an old legacy application or a system management mode handler that might have variables and code interleaved. So basically the goal was we wanted to look at one page of an executable that we didn't have access to the source code for that may have variables that are originally, say, initialized to 0. And so when we hash that before we run it, we get one version. But then as it starts running, it's going to gain this dynamic state because the instructions and the code are interleaved with the data. And so then when we hash it again, we get a different result. We're not sure if that's because those variables are just changing as part of normal execution, or if it's been subverted or a code injection attack. And so basically the question is we see a little change right there. Has this executable been modified? And so that's kind of what the whole goal was for this. So starting from Shadow Walker, we ran into a couple challenges, which I'll go through really briefly and how we kind of overcame them. This is more about MoRE and less about how this impacts x86. So the first one was the STLB. We started off implementing a page fault handler hook, very similar to Shadow Walker. Then we ran into some issues with the Windows 7 memory management, the TLB being cleared on every VM exit or VM resume, and then Windows copy and write, which is kind of a funny one as well. I've already clarified this, so basically we had to go through and hoist our page fault handler up into an EPT. So we created a thin hypervisor, about 2,000 lines of code with EPT and VPID support that would allow us to do an identity map. So this is not a hypervisor like Zen or VirtualBox that allows you to run multiple different guests. This is basically just you have one guest, your Mac or your Windows machine, and this is just running up there as and letting all your device accesses and your devices talk directly to the hardware and to the operating system. And so basically from that execute only, the STLB will not merge entries with conflicting permissions. So if you prime the instruction TLB with an execute only thing, an execute-only mapping. When the data TLB asks the STLB, it'll say, well, yes, I have one, but it still won't help you because this is execute only, so you're still going to have to fault. And then I still will be able to trap that fault and then either set up the data one, or if it was like a PAX, no execute one, just deny that. So Shadow Walker was focused on a memory hiding rootkit for kernel code, the FU rootkit. Kernel pages are rarely, if ever, paged out to disk. What we were doing is our test program was something we wrote, just a Windows C++ program, which does get paged down and out. If you're running low on memory, it might get paged to disk if it's not actively being used. So that was an issue we had, where sometimes we would be paging out memory, but it was still in memory. We were just marking it as non-present so we could trap on that. And then we would actually go and try to split it, everything, and then we'd realize that Windows had actually paged that memory out and it was on disk somewhere, and we would just crash the program. And then also, when you start mucking with the paging structures for user space applications, Windows gets a lot more finicky. I would say that Windows XP had a very much more laissez-faire approach and would kind of let you do whatever you wanted to. Though it appears to us from our development of moving from Shadow Walker and Windows XP to Windows 7 that somewhere in between that, the MS kernel team read a book on programming, and now they check their data before they just blindly jump to function pointers and stuff. So kudos to them, though it is a little more painful for us who aren't blessed with the source code to Windows, that we have to figure some more stuff out on our own. As I mentioned, we use EPT. Thanks to Intel for providing a solution around this. So here we and the hypervisor have our own set of page tables. We use the extended page tables, we modify our own stuff, and then the operating system has their page tables, they modify their things there, and they each work in their own little isolated bubble. And so the operating system doesn't affect us, and then we don't have to worry about the operating system doing stuff and complaining that we've changed their page tables. Also with the EPT, we're preempting the operating system page fault. So an EPT fault will trigger before a page fault. I mentioned already the TLB is cleared on a VM exit and VM resume. So when we were testing this, it was a 4-month effort. We sent down the test code and it was working great. And we didn't realize that half of our test machines were Core 2 Duo and the other half were Core i7s. And so it was working great for us, and they said it's not working. And so one weekend of figuring out all this, we were running into an issue where we would prime, say, the data TLB in the hypervisor. We would resume back to the guest, and it would be wiped. And then the guest would say, nope, you didn't do it, fault back. And so we'd just hang forever. So again, thank you, Intel, for VPID. Not only does it make us faster, it allows us to bypass that. So the last major challenge we ran into, this is more about the MoRE effort specifically than TLB splitting in general. So Windows generally loads one copy of the executable pages into memory, so it can deduplicate. If you're running 10 instances of Notepad, it can just run one instance of the executable page and then 10 instances of the data copies. And then they can perform copy and write if, say, there's a self-modifying Notepad, which sounds pretty terrifying. Our test application we wrote specifically interleaved code and data. So we wrote a huge NOP sled, and we used that as our memory buffer for all of our work so we could actually simulate what this would be. So we were always triggering that copy and write, and then Windows would say, oh, no, we need to keep that pristine copy here where you know it is, and we're going to move the copy that we're actually going to work on that might be subjugated somewhere else. We're not going to tell you where it is. So now we were TLB splitting on a page that wasn't being used, which was doing effectively nothing. And so we had to find wherever our application went. So our really ugly solution was we would trap on a context switch and then rewalk the page tables for our application to see if they had copy and write had occurred, and then we would go and update which pages we were splitting on. Not very graceful, but it worked in the 2 months that I had to do this. So real simple, STLB we overcame by using EPT, which has the more granular permission set. The Windows 7 memory management, again EPT. TLB being cleared on a VM exit and VM resume, we implemented VPID tagged TLBs, and then the Windows copy and write, we just brute force walking the page tables to make sure we can keep up with everything. Everyone good so far? Perfect. Yeah. Do what? So that came back to this goal right here of we wanted to look at an arbitrary binary and say this thing which may have data and code interleaved on the same memory page, has it changed? So this is a defensive application. So if you're familiar, in a system management mode kind of is like BIOS that runs persistently. And if you look at how the STM, the software management mode transfer monitor, which is a hypervisor that runs in SMM space, when you kick off a TXT measurement, unless you have that STM doesn't really measure the SMM handler because it might have some dynamic state and it's a legacy application that's interleaved. In this case, the STM could actually do this kind of TLB splitting and could actually use a legacy SMM handler but still get consistent measurements that when you do a late launch TXT measurement, you can actually verify all the code rather than just relying on your hypervisor security in your SMM, your STM. Did that answer that? Okay. The question was, what's the point of doing all this? So. Oops. So what did we do? In about 2 months, we built a custom VMX hypervisor that we added EPT and VPID support that we could monitor process creation. So we were doing it all in Windows just to make it nice and easy. We had a list of file names, so like test.exe, etc., that we would trap on. We want to split the TLB for. And so we would monitor whenever a new process was created. This was all a Windows kernel module. Then we would VM exit on either a CR3 change, so we could walk through and look for any Windows copy and write activity, EPT violations and faults, which would go and we'd actually do the real splitting, and then the trap flags that we could we could presume and single stepping after we either prime the data or the instruction TLB of the guest. So like Shadow Walker, this is very obvious here. Basically, if it's a data fetch, we're going to mark the EPT pages for that page as read-write and allow it for one instruction. If it's a code access, we mark it execute only for one instruction. And then we ran into this very interesting case for both. So we call these thrash cases, where there was an instruction on a certain page, maybe like the first instruction of the page, that is also referencing memory on the same page, and neither of them are in the TLB. And so it's asking for both at the same time, and it would kind of flip-flop back and forth. And so what we had to do here to get kind of through these, they're very rare. There's maybe over a duration of a program, maybe there's a couple hundred of these thrashes that we ran into. So only a couple hundred instructions would hit this case. And so what we would do is we would copy one instruction from the pristine, known good executable copy to the data copy to ensure that there hasn't been any compromise there. And then we would run it with full permissions for one instruction, and then we would reset it to no permissions and clear the TLB. So this allowed us to kind of break through those weird thrash points. So that's kind of just a weird one that we would kind of occasionally have this weird issue where it kept switching back and forth, where it was asking for data and then asking for executable and vice versa. So our results, we were hitting about less than a 2% performance hit on our test cases. Most of that comes from just kind of the upfront cost of setting up the TLB split. So the longer the program ran, the runtime hit was very, very small. We had one program that was almost too short to measure, even running by itself, so it showed up as a 98% performance hit just because you're talking about fractions of a second. We architected our hypervisor to have clear isolation of data and code, so something else could measure us. So if you fired off a TXT late launch, you'd be able to measure our code sections and make sure that it hasn't changed. And then also we could then re-verify, measure the trust of our application of test every 1/10 of a second was just some number I threw in. And as long as you weren't printing the results over debug view, it would work very quickly. The second you tried printing out every 1/10 of a second, the system crawled to a halt. And this was all with no modification of the application. So this is perfect for a legacy, BIOS. So we just we had one person write an exe, and then we had one person, me, write the hypervisor for it, and we weren't allowed any recompilation or source access. So I have a very not so interesting video for you. So as we mentioned, dynamic applications kind of gain state as they execute, and this is these variables that are changing. And so on the right here is just a program we wrote. It just calculates pi very slowly, and all the variables are written to, let's see, can I pause this? Into our no-op sled that we put in. So this is a special application as well. You had to modify some of the PE flags that it would actually allow you to do this. Otherwise, the Windows would shut down the application. So here we have some stuff over there, and you'll notice on the left, I'm not sure how well you can see it or not, but the checksum is changing. You can take my word for it that essentially what we're doing is we're noticing that the checksum is changing as this application is gaining dynamic state. So now what we're going to do is we're going to leave that application on the right unchanged, and we're just going to turn on the TLB splitting feature of the hypervisor. So you'll notice on the left, once it starts printing stuff out, it's going to print out a data copy and an executive copy. And so you'll see the data copy is changing as it should, variables change, etc. But we're automatically kind of isolating the data and the instruction. And so the executable checksum will never change as it's run, but the data checksum changes. So we're basically transparently separating them out. Very good question. So with this, we actually created a second mapping in EPT for our hypervisor to be able to get to that and as read-only, because that mapping was completely different. So we had to have like a second mapping to the executable page. Otherwise, we would go through the same process. Additionally, since we're running in the measurement routine right here coming through is happening in the hypervisor context. So it's a different VPID. It's just being piped through to debug view in the guest. But yeah, very good question. Against what? Oh, I'll get there. So with that perfect segue, MoRE Shadow Walker. So as Dan Gear very eloquently pointed out yesterday, there's a lot of dual use technology. So every tool you have out there you can use for good or evil, so to speak. And TLB splitting is a perfect example of this. You can use it for offensive or defensive, as we've shown with PAX and MoRE as being defensive, and then Shadow Walker and now MoRE Shadow Walker with the offensive. So basically what I did is I just took out all the trusted computing stuff in the MoRE hypervisor, and it allows you to do essentially the same thing as a Shadow Walker. And so this would, in theory, be able to bypass PatchGuard, because when PatchGuard or any other kind of kernel integrity monitoring is going to read that, they will read the unchanged version, but if they actually jump to that to execute, they will execute. So basically the gist of this is you can split arbitrary pages on a new Nehalem and newer CPU. Any other questions? There's one question I'm hoping someone's going to ask right now. Perfect question. So what's the point, right? Why bother? If we already have VMM, like we're blue pill, right? Why would we bother? You don't need to have a memory hiding rootkit. You just set up your EPT and then you just make sure that the the operating system can never read your memory. So there's a couple reasons for that. One is the closer you are to the user and the application and the operating system, you have more control. You can kind of introspect on certain things, like someone opens up a certain file and you want to inject content into it, or say you're a keyboard logger. You want to be able to hook the keyboard driver, and then you want to be able to use the kernel network stack to exfiltrate that data. You can do all that from a hypervisor, but it requires kind of emulating. It requires kind of writing your own network stack. So with blue pill and red pill, so red pill was an anti-blue pill detection technique. What they did is they found really the only way you can detect if you had a really good hypervisor is looking at the performance hit of some simple operations. So one example, the CPU ID instruction will always trap to the hypervisor. And so usually it takes like 7 clock cycles, but now you're doing an entire context switch to a hypervisor take a lot more. Okay. So the less stuff you have in VMM, the better. And so this also can be applied to system management. I mean, I've written a system management mode rootkit, but once you're up there, I mean, yes, you have full privilege and you can do anything, but that means that you now need to like write your own operating system, your own network stack to be useful. And so also you have just a huge library of existing stuff out there that you can just kind of reuse. There's a whole bunch of really cool rootkits out there. A lot of them you can find the source for. You just kind of wrap this up in the MoRE Shadow Walker and you're good to go. And then also just the last one, just synthetically, just to show you that it can be used, for good or evil, depending if you're a merchant or death or a white hat. So that I'm just going to kind of conclude that the gist of this is that x86 has gotten so complicated that you can now affect huge apparent architectural modifications. So in this case, switching from a von Neumann architecture to a Harvard architecture or an apparent Harvard architecture just through software. So a lot of researchers, they use OpenSpark, which is an FPGA, and so they can make different changes to how certain things happen. A lot of this now can be done through software. I would really be interested in someone writing a thin hypervisor research idea for any grad students that can, on an SMP system or a couple SMP systems, can boot up and appear to look like a NUMA system where you have your memory zones kind of isolated to each of your clusters. So you'll be able to boot one operating system across multiple machines in a single system image. Another example of the complexity, the memory management unit is actually Turing complete on x86. This was shown by Sergey Bradis and Julian Bangert, showing that you can configure your page tables in such a way and then cause a page fault and simulate any Turing machine without ever executing an instruction. So you don't even need a CPU to be able to run programs on x86 because the memory management unit is so complicated. And this is happening over and over and over again. These weird machines pop up everywhere. And then also, just as architecture evolved, and as there's this cat and mouse game of the offense versus the defense, new techniques come up to bypass things. So this is a classic example. The NX bit came out and stopped the classic smashing the stack attack. And now you have ROP, and then there's Emmet. And I just saw a great talk yesterday about getting around Emmet and still being able to do ROP attacks. And so really this just shows that, as the things progress, don't give up as soon as they say, okay, we fixed this exact technique. And so there's probably a new way to do it. The code for both the hypervisor that was submitted to MUDGE for Cyber Fast Track that does all the trusted computing and measurement, that's going to be released open source, as well as the very simplified one that just you give it a virtual memory address and then the code page you want it to go to and the data page you want it to go to, and it'll do the splitting. That's going to be on this address. It's released this week, and since this week is not yet done, I actually haven't uploaded it yet, so it will be there by the week's end. A couple shout-outs, so GR Security and PAX team for making Linux more secure, being way ahead of the curve. Jamie Butler for providing some guidance on the CFP program and how to get into Black Hat. And then Mudge, he was at DARPA, now he's at Google or Motorola, for basically taking more from just an idea in my head to reality. And then my employer, AIS, for putting up with me when I disappear off to the third world for a month at a time. So with that, thanks for listening. You guys can now heckle and any rotten fruit. And then I'm here all week, so if you want to meet up or chat, shoot me a tweet and go from there.